Welcome back. In this video, we want to look at explainable machine learning with cyclic boosting. Cyclic boosting is essentially a machine learning model that falls into the category of generalized additive models. It's sort of an extension of linear regression, but sort of linear regression on steroids. Remember, linear regression looks essentially like this. You have a prediction y hat, and then essentially a sum over all your feature variables x with some sort of weight alpha plus some term beta. And the generalized additive models follow the same thing, but instead of having y directly, we model the expectation value and have a link function, and then we have some sort of generalized function that operates on our feature variables. So let's look at the code. If you don't have it available, you install it, and we import the relevant libraries, essentially all the details from cyclic boosting. And then as a data example, we use the adult data set that focuses on binary classification, whether or not a person makes more than $50,000 per year. It's a fairly old data, so you should take the $50,000 a year with a grain of salt. We can read it from the web directly, so we don't need it locally, and the columns are described like this, and we have categorical variables which we define here as well. And then if we look at the data frame, it looks like this. So we have a number of rows, each correspond to a person, the given age, working class status, education status, and so on. As always, when we start with machine learning models, we do some exploratory data analysis. So for example, we can look at education, and then our target is income below or greater than 50,000. You can see that education does have quite an impact on that. Or we can look at the marital status. You can see that the outcome depends on this as well, or the gender, or the race, or the occupation, like your work. You can see that all of those have quite a strong input on whether or not your income is around 50,000 more or less. You can also then see how the hours worked per week depend on this. And now that we've built an understanding of our data, we prepare the data for the machine learning. So we have our categorical columns, so everything with type category is one of those. And then we apply a preparation code. Here we convert all text to numerical values. We can do this efficiently with a lambda function, then call apply, so that pandas does this for us. And we can also then convert the target column, which is smaller than 50K or larger, as the text. Now we can do this as a number, and we can also do this again with the lambda function and apply. And we say everything but the final column where our target variables is our training, and then we have our data frame for the income that is our target variable. And so after all of this has happened, we can see that our data frame is now full of numerical values and no longer text. Then we split this into test and train data, 75% as the split. And one of the features of cyclic boosting is that we can have specific details, or we encode specific details that we know about our data set. So if, for example, if we have a category, or if we have a continuous variable, we can say that this is a continuous variable, or it's an ordered or unordered list, and so on. In particular, what's important is that we have missing values, and cyclic boosting knows how to handle missing values, that these are special cases, so we don't have to do this ourselves. So for each of those, we set appropriate flags. So for example, working class is an unordered class. So for example, one job isn't necessarily better than the others, but they are distinct. It does have missing values, and we don't want to learn those. And we do this for all of those. So we have the categorical variables. We have one which is ordered. For example, a bachelor's degree has less educational value than a master's degree or a PhD. So this is an ordered class. And then we have age as a continuous one. Now we set up our model. So we take our cyclic boosting classifier and pass it the description of our feature properties and call the fit method and get the predictions. And following the scikit-learn convention, we have predict and predict proba, and we add this to our data frame. Now we want to evaluate how this classifier works, and we build the confusion matrix. Ideally, as we know, this should be more diagonal. We have the metrics that we can calculate, and we build the ROC curve, and you can see that this behaves quite well. So far, this is all sort of standard machine learning, and now we come to the explainable part. So we can get the feature contributions and see how all of the features are important for the test data that we want to evaluate on. So we can print all of them, and that gives us then a long array, but now we can make use of the convenience functions and plot the feature contribution. So we take, for example, prediction index at 12, or you choose something else, and we have the number of variables that are there, right? And then we can loop over them, and if we pass a threshold, then we can also change the color to indicate that this is a very important feature. Now there's some more magic to set up a nice plot, but what comes out is that we have a value here with a neutral one, and we can see how far this deviates, and the larger the bar to the left or to the right is, the more the individual variable for this specific prediction will pull in one or the other direction. And if you change the prediction index above, then this will change, because then this will then apply to a different row in our test data set.